simply supported beam with central point load. To begin the experiment, a mild steel beam with a length of 80 centimeters, a width of 3 centimeters, and a thickness of 3 millimeters was selected for testing. The beam was placed on 2 supports at both ends, creating a simply supported beam condition. The supports were carefully aligned to ensure stability throughout the experiment. Next, a dial gauge was positioned precisely at the center of the beam span. The gauge was aligned with both the longitudinal and transverse center lines of the beam to accurately measure the vertical deflection. The loading hook was also positioned at the center so that the applied load would act exactly at mid-span. Before loading, the apparatus was checked to ensure proper alignment and to minimize measurement errors. The experiment was then carried out by gradually applying loads at the center of the beam and recording the corresponding dial gauge readings. For the first loading stage, a load of 1.0469 kilograms was applied. After the beam stabilized under the load, the dial gauge reading was recorded as 22 plus 68.9 divisions. The load was then increased by adding an additional 1 kilogram, bringing the total load to 2.0469 kilograms. The resulting dial gauge reading was recorded as 20 plus 37 divisions. For the third loading stage, an additional 2 kilograms were added, increasing the total load to 4.0469 kilograms. The dial gauge reading was observed and recorded as 15 plus 98.1 divisions. The loading process continued by adding 4 more kilograms, resulting in a total load of 8.0469 kilograms. Under this load, the beam experienced a larger deflection, and the dial gauge reading was recorded as 8 plus 50 divisions. Finally, an additional 8 kilograms were added, increasing the total load to 16.0469 kilograms. At this stage, the beam deflected beyond the measurement range of the dial gauge. This indicated that the beam had reached a deflection greater than the instrument could accurately record, demonstrating the significant effect of increasing load on beam deformation. Throughout the experiment, it was observed that as the applied load increased, the beam deflection also increased. This behavior agrees with beam bending theory, which states that deflection is directly related to the magnitude of the applied load within the elastic range of the material. The collected measurements were later used to compare the experimental behavior of the beam with theoretical predictions and to evaluate the accuracy of the beam deflection equation for a simply supported beam subjected to a central point load. This experiment successfully demonstrated the relationship between load and deflection and provided practical insight into the structural behavior of beams under bending loads. Cantilever beam with endpoint load. After completing the simply supported beam experiment, the beam was rearranged to create a cantilever beam setup. A steel beam with a total length of 80 centimeters, a width of 3 centimeters, and a thickness of 3 millimeters was used. Approximately 40 centimeters of the beam was rigidly fixed between supporting blocks, while the remaining 40 centimeters projected outward as the free cantilever span. To measure the beam deflection, a dial gauge was installed near the free end of the beam. The gauge was positioned along the center line of the beam width and approximately 5 centimeters from the free end. The loading point was also located at the same position to ensure accurate measurement of the vertical displacement caused by the applied load. Before applying any load, the initial dial gauge reading was recorded as 21 plus 63.3 divisions. This reading served as the reference point for all subsequent measurements. The experiment was then performed by gradually increasing the load at the free end of the cantilever beam and recording the corresponding dial gauge readings. For the first loading stage, a load of 0.7163 kilograms was applied. The beam immediately showed a measurable downward deflection, and the dial gauge reading decreased to 18 plus 99.6 divisions. For the second loading stage, an additional 0.25 kilograms was added. As expected, the beam deflected further under the increased load, and the dial gauge reading became 16 plus 24 divisions. The load was then increased by another 0.25 kilograms for the third reading. The resulting dial gauge measurement was recorded as 14 plus 37.2 divisions, showing a continued increase in beam deflection. For the fourth loading stage, an additional 0.5 kilograms was applied. The total load on the beam increased significantly, and the dial gauge reading dropped to 11 plus 83.8 divisions. Finally, an additional 1 kilogram load was added, bringing the total applied load to approximately 2.7163 kilograms. Under this loading condition, the dial gauge reading was recorded as 5 plus 89 divisions. Beyond this stage, further loading caused the beam to deflect beyond the measuring range of the dial gauge. The displacement became larger than the instrument could accurately record, indicating a substantial increase in beam bending under the applied load. Throughout the experiment, a clear relationship between load and deflection was observed. As the applied load increased, the free end of the cantilever beam experienced progressively larger deflections. This behavior is consistent with the principles of beam theory and demonstrates the sensitivity of cantilever structures to loading at the free end. Compared to the simply supported beam tested earlier, the cantilever beam exhibited noticeably larger deflections under relatively smaller loads. This is because one end of the beam is completely fixed while the other end remains unsupported, creating a structural condition that is more susceptible to bending. The recorded measurements were later used to compare experimental results with theoretical predictions and to evaluate the accuracy of the cantilever beam deflection equation. Overall, the experiment successfully demonstrated the behavior of a cantilever beam subjected to an endpoint load and provided a practical understanding of structural deflection under bending forces.